Day 4 of writing an onset detector. Now that I'm finally done with SysX, at least I hope so, I can finally focus on the onset detection itself again. And last time I wrote the onset detection, it didn't look very good, but today I made a lot of progress, which I'm going to show you today. So first of all, a little reminder, this is a beat. And this beat has the nice property that it has one chunky big kick at the beginning and a randomized hi-hat, which is all very challenging for an onset detection. So this is a great example beat for the things that we are going to do today. So one big difference between how it was before and now is that I now separated different tasks to different classes that don't have very meaningful names yet, but onset detector is basically like the core onset detector. It just has the 2 envelope followers, it has a buffer that it can use, and it has a resonator to reduce the frequency to a specific smaller part of the spectrum, and also has a gain value now. And I made this separation because I decided to have an onset detector 2 class, which has 32 bands ranging from 1000 to 50,000 hertz. So it's an array of onset detectors. Each of these has its own resonator and 2 envelope followers and stuff. And now that enables me to make sort of a pseudo multiband thingy. And I have various debug modes that I use to visualize my onset detection into an oscilloscope in Bitwig. So we are going to start with debug ratio sum, and it looks like this. So as you can see, this just creates a very nice curve. It is the ratio between the envelopes, just like before, and it shows the points where there is an onset very clearly. So that's pretty cool. As you can see, it is a parallel processing thing right now. The buffer of the overall class is being cleared, and then I'm looping through all of the detectors. Each of them does the thing where you take both of the envelope followers that have already measured their envelopes, and then you take their values for a specific sample index. Then you take the ratio between that and you multiply it with your gain value. That's it. I changed something about the way attack and decay works. Now there is an attack value, but it's not in hertz or milliseconds or something, but actually just in percentage, because the milliseconds value is derived from the frequency of this onset detector. Because the onset detector has a resonator, and the resonator is kind of the frequency of this whole thing. You can see it like this. The wavelength of this frequency could be used as an attack value, but it could also be multiplied by some value to give an offset from that. And it's the same for the decay, for both of the decays. Actually made a little mistake here by keeping the times 0.5 in there. So I have to change that still. You can also change the cutoff frequency. The bandwidth is currently fixed to 1000 Hertz, but I'm going to make that a parameter as well again at some point, I guess. And there is now a tilt parameter, which is like sort of a tilt EQ, but it's not applied on the main signal in general. It distributes gain values across the onset detectors, as you can see. Lowest gain and the highest gain, and there are minus the decibel and plus the decibel parameter that goes in here. And then yeah, it does the thing, because I felt like onsets are often the moments where there is more high frequency content. So if we give it a little bit of a tilt, then we make the high frequency content more important to the algorithm, which helps it pick up the onsets. So this curve is the sum of all of these onset detectors. It's not a single onset detector anymore, and because of that it is much more balanced than what you can usually do with a single onset detector. Let's play around with the tilt parameter a little bit to see its effect. As you can see, with more tilt it's much more easy to see where the onsets are, because they clip 0 decibel. But also it pushes some of the other noise. So if we dial it back again, we get a nice compromise that could be useful. Maybe something like that. Okay, let's check out the second debug mode, which is called debug ratio max. Alright, next up we have debug ratio max, which works like this. We are looping through all of the samples, and then for every sample we loop through all of the bands and process one sample with our onset detector, and then we check out if this value, which starts at 0, is smaller than whatever the detector currently detects. And if yes, then we update that and we save the index value, because at the end we use a ratio between the index and the number of bands to output it into our oscilloscope, and that is what we get as a result. And even in this signal, which looks very different than the one before, we can clearly see that the onset is the one where it goes up the highest. Like this, and this. Unfortunately, the noise is also pretty high, so I don't know if this could be improved or something. Of course, another alternative would be that we actually write the max value in here and see where that goes. I think that this would create a very discontinuous curve, but I mean, using index values also does that, so let's try that. Oh wow. In some sense that is even more perfect than the other one because it like suppresses the noise much more, but the peaks don't go as high anymore. That's kind of weird. Let's try if we can find a better setting for this. Let's go. That looks pretty good. Yeah. Alright, that's definitely better than the index stuff. So as you can see, this is still very work in progress, very experimental. I'm changing things on the fly. By the way, if you're wondering why can I take the max without ABS, the reason for that is because a long time before I rectified the signal so that I don't have to deal with rectifying in the middle of the process anymore. Alright, and now we go to the last debug mode, which is debug Spec Env, an idea that I had lingering around in my mind for a while now. This mode is also very similar to the one before in the sense that we are looping through the samples using the detector, processing the sample and then doing some process and then outputting the ratio between the index and the number of bands into the buffer. But the difference is that in this case we are not looking for the maximum sample, but we are looking for any sample that is higher than some arbitrary Spec Env threshold value. And if yes, then we are updating the index. So basically, whenever there is a frequency that is higher than the frequency before that also exceeds the threshold, then take the higher frequency, because higher frequencies have a tendency to be shorter. So if we want to detect very fast envelope changes, then that could be useful, I think. When Spec Env's threshold is 0 decibel, we don't see anything passing through the algorithm. But when we turn it down, we can see some things appearing and we can already see, alright, so there are our transients basically, and they are very clean popping up, very cleanly popping up. If we turn it down even more, then it gets messy. But yeah, there is some inconsistency in that as well, and sometimes the peaks are even detected a little bit too early, so that could get annoying for sure. Now, just out of interest, we could also just put the value that we are interested in. So let's find out what that would be like. Now that is interesting. Now we don't get the same type of noise suppression that we would get if we, well, just cleared the entire thing whenever it is below the threshold. Now we get something that just looks very similar, and it still highlights the peaks. We could easily just set a threshold here and say, yeah, when it has exceeded the threshold, then that is a peak. So that could be seen as a success, but the other one was better in this case. Yeah, that is the current state of the onset detection for now.